A wondrous day to all dear enthusiasts. I hope that you guys are having a great time today because it's such a vital instrument for us to wear with optimism amidst our individual torrential period. So, for today's expedition, we will be traversing the chapter 13 topic within our class ebook. The topic waiting lines and queuing theory models. At this point, I am humbly presenting to you guys the presenters, or should I say the enthusiasts of our group. Let's start with Miss Shohani Al Sema, Miss Bay Shohani B. Angas, Miss Bay Rahamina Mluk, and of course, yours truly. Let's take a look for our learning objectives. Of course, it is beyond imperative for us to know and to present them before starting or sort of like formulating the actual discussion that we will all be traversing. First up, describe the trade-off curves for cost of waiting time and cost of service. Understand the three parts of a queuing system. These are the calling population, the queue itself, and the service facility. Next up, describe the basic queuing system configurations. Understand the assumptions of the common models dealt with in this chapter. And analyze a variety of operating characteristics of waiting lines. Don't worry, we got you guys. It might be a little confusing or it might be a little tricky for you guys to comprehend this posted learning objectives, but my group could assure to serve knowledge with such an abundance of gratification, or should I say, an abundance of assurance. So as you can see here, we have here our chapter outline. So we have, or we will be discussing the introduction, the waiting line costs, characteristics of a queuing system, single channel queuing model with, okay, this one might be a little tricky for you guys to understand or to read because it looks like the spelling could be pronounced as poison, but it's actually poisson. Okay, so it will be like single channel queuing model with Poisson arrivals and exponential service times. Multi-channel queuing model with Poisson arrivals and exponential service times. Constant service time model and finite population model. Of course, we have here also the some general operating characteristic relationships, and the last but not the least, more complex queuing models and the use of simulation. So without further ado, let's now start diving in with the introduction of waiting lines and queuing theory models. But by the way, I have a little trivia with you guys. Ostensibly, this can't be found within our ebook material. But since I had to take a massive research with regards to our presentation, I also had a chance to pick up who invented queuing theory. So who invented queuing theory nga ba? He's no other than Agner Krarup Erlang, a Danish mathematician, statistician, and an engineer. He's credited with, creating not only queuing theory, but the entire field of telephone's traffic engineering. So as we can see here, the study of waiting lines is called queuing theory. Well, actually, this is one of the oldest and most widely used quantitative analysis techniques. According to statistics, it is the study of the movement of people, movement of individuals, objects, or information through a line. From the word itself, waiting line. So, yung waiting lines are an everyday occurrence. So, it affects people shopping for groceries, buying gasoline, making a bank deposit, or waiting on the telephone for the first available airline reservationist to answer. So, furthermore, it examines every component of waiting in line. So that includes the arrival process, yung mga iba't ibang processes, service process, number of servers, number of system places, and the number of consumers, which might be people, individuals, data packets, ano pa ba, cars, or anything else. So this is drastically and authentically happening every single day within the sphere of reality. Literally, the real-life applications of queuing theory encapsulates a wide range of businesses. So yung mga findings na to may be used to provide faster customer service, increase traffic flow, ano pa ba? Improve order shipments from a warehouse, or design data networks, and also call centers. So ngayon, balik tayo dito sa presentation natin. Yung queues, what is it all about? It's about, it's the another term for waiting lines. As what I'm saying earlier, or the point of what I was inducing earlier, it may also take the form of machines waiting to be prepared, trucks in line to be unloaded, or airplanes lined up on a runway waiting for permission to take off. Ngayon, so since nga yung ating queuing models or queuing systems is up and analyzing how customers receive a gratifying service, we have here the so-called three basic components of a queuing process. So ano-ano nga ba ito? Tatlo sila. First is the arrivals, service facilities, and yung actual waiting line. In arrivals, or also known as arrival process, this is simply how customers arrive. Take for example, ano nga ba yung sa isang fast food chain. Yung mga customers na nag-a-arrive in one place, pumupunta sila mismo dun sa cashier for what? For what reason? Syempre para mag-order, to have the product that they are demanding, or specific item or food that they are up in cravings. Yun yung dahilan kung ba't sila pupunta doon para kakain. So in order for them to have the product, the item, syempre pipili sila doon. Yung process pa lang na yun ay tinatawag ng queuing process. No? So they may come into a queue alone or in groups. Kasi nga, di ba, sometimes kapag pumupunta tayo ng mga fast food chain, it's either we are alone or we are accompanied by our friends, family, or any camaraderie that, malapit sa ating puso at buhay. And they may arrive at certain intervals or randomly. Next up is yung tinatawag nating service facilities. So in this part, it just simply showcases or simply embraces how customers are serviced, or how customers are being rendered by service. This includes the length of time a customer is serviced, the number of servers available to help the customers, whether customers or yung consumers are served one by one or in batches, and also the order in which customers are serviced. Dito rin papasok yung tinatawag nating service discipline. So what is this all about nga ba? So it simply refers to the rule by which the next customer is selected. Although many retail scenarios employ the first come, first served rule, other circumstances or situations may call for other types of service. So magbigay tayo ng isang example. Example, customers may be served in order of priority, or based on the number of items they need serviced, such as in an express lane on a grocery store. Sometimes, the last customer naman, or the last item na kailangan i-render ng service na darating, is yung mauuna or will be served first. Ano yung example na to? Example, sa isang case ng stock of dirty dishes. Di ba kung ano yung darating recently na mga huhugasin is yung mga items na mauunang ma-renderan ng service. Bakit? Kasi syempre yun yung mga nasa top eh. So kung huhugas ka, hindi ka naman pwedeng kukuha dun sa baba. Kasi masisira yung arrangement or sometimes it might cause trouble pa na mahuhulog yung mga furnitures. Yung mga plato. So, ganun. Mauuna yung nasa recent, yung nasa top, na mahuhugasan. Dito rin kasi pumapasok yung FIFO, LIFO, and also yung priority sa service facilities. Yung FIFO is yung, alam naman natin lahat tayo dito ay medyo familiar. Yung first and first out. Yung LIFO naman is yung last and first out. And also yung priority. Alam natin to from the word itself, priority. Yung customers are served in order of their importance on the basis of their service requirements. And of course is yung ating actual waiting line. Okay, I'll just add more information by this one. By adding queuing theory kasi, a business or an organization can develop more or advance more efficient systems. Also the processes, pricing mechanisms, staffing solutions, and yung arrival management strategies to reduce or to somehow reduce customer wait times and increase the number of customers that can be served. Okay? So ngayon, let's move on to the another slide. Okay. So in this chapter, we will further also discuss how analytical models of waiting lines can help managers evaluate the cost and effectiveness of service systems. Next up, we begin with a look of waiting line costs and then describe the characteristics of waiting lines and the underlying mathematical assumptions used to develop queuing models. We also provide the equations needed to compute the operating characteristics of a service system and show examples of how they are used. Later, we can see that one, or we can discuss that one. And also, in this chapter, you will see how to save computational time by applying queuing tables and by running waiting line computer programs. Now let's all proceed to our next subtopic, which is the waiting line costs. As we can see here, most waiting line problems are centered on the question of finding the ideal level of services that a firm should provide. So ayun na nga. If you guys can all notice, or kung mapapansin ninyo, masyado na tayong redundant when it comes to like the information that you guys are all getting from me, or even in the slides here. It's all redundant, right? Isn't it? That is because ito talaga yung context, yung major concept ng ating waiting lines. So to add up more information, let's just provide more examples. First, yung mga supermarkets, they should decide or they must decide how many cash register checkout positions should be open. Also, the gasoline stations out there, they must decide how many pumps should be open and how many attendants should be on duty on that specific day or on that specific expedition. Also, yung mga manufacturing plants natin, they must determine the optimal number of mechanics to have on duty each shift to repair machines that break down. And also yung mga bangko, yung ating mga banks here, they must decide how many teller windows to keep open to serve customers during various hours of the day or of that specific expedition of that activity. Isa kasi talaga sa mga major goals ng ating queuing analysis is to find the best level of service for that specific organization or a business firm in general. So in most cases, this level of service is an option over which management has control. An extra teller, for example, it can be borrowed from another chore or it can be hired and trained quickly if demand warrants it. This may not always be the case though, A plant may not be able to locate or hire skilled mechanics to repair sophisticated electronic machinery. When an organization does have control, its objective is usually to find a happy medium between two extremes. Una nga is yung ating firm. If a firm can retain a large staff and provide many service facilities, of course, undoubtedly, this may result in an excellent customer service. Kasi syempre, if you will be providing more or massive service facilities, of course, magiging or magre-result ito into another excellent performance with seldom more than one or two customers in a queue. Of course, by that, customers are kept happy. They are kept satisfied and gratified with a quick response and appreciate the convenience. However, on the other side, this can be much more of like expensive. Kasi syempre, if you will add more service facilities, you should invest more. You should provide more. Yun lang. Meron talagang bagay na kailangan mong paggagastusan if you really want to have that gratification from within. So the other extreme is to have minimum possible number of checkout lines, gas pumps, or teller windows open. This, however, keeps the service cost down, but may result in customer dissatisfaction. Syempre, kokonti yung service facility mo. Kokonti yung mga progress na mangyayari since yung service facility mo is magre-reduce din. Of course, undoubtedly, magre-result talaga siya sa magre-result talaga siya into customer dissatisfaction. As the average length of the queue increases and poor service results, customers and goodwill may be lost. Okay, most managers recognize the trade-off that must take place between the cost of providing good service and the cost of customer waiting time. The latter may be hard to quantify. They want queues that are short enough so that customers don't become unhappy and either storm out without buying or buy but never return. But they are willing to allow some, waiting in line if it is balanced by a significant savings and service costs. One means of evaluating a service facility is thus to look at a total expected cost. So, yung concept na naka-illustrate dito sa figure na ito, yung total expected cost, para makuha yan siya, we should get the sum of expected service costs and expected waiting costs. So, it would be expected service costs plus expected waiting costs. That would be equal to total expected costs. So, yung service costs are seen to increase as a firm attempts to raise its level of service. As service improves in speed, however, the cost of time spent waiting in lines decreases. Basta tandaan lang natin, the goal is it is oftentimes to find the service level that minimizes the total expected cost. So we have here our example, Three Rivers Shipping Company. So allow me to read this one to you guys. Three Rivers run a huge docking facility located on the Ohio River near Pittsburgh. Approximately 5 ships arrive to unload their cargoes of steel and ore during every 12-hour work shift. Each hour that a ship sits idle in line, waiting to be unloaded costs the firm a great deal of money, about $1,000 per hour. From experience, management estimates that if one team of stevedores is on duty to handle the unloading work, each ship will wait an average of 7 hours to be unloaded. So if 2 teams are working, the average waiting times drops to 4 hours. For 3 teams, it's 3 hours. And for 4 teams of stevedores, only 2 hours. But each additional team of stevedores is also an expensive proposition due to union contacts. So Three Rivers superintendent would like to determine the optimal number of teams of stevedores to have on duty each shift. The objective is to minimize total expected costs. This analysis is or will be summarized in the next table. Gaya nga ng sabi ko kanina, the goal is always to find the service level that minimizes total expected cost. So now let's take a look to our waiting line cost analysis or yung table analysis ng Three Rivers Shipping Company na in example natin earlier. So technically speaking, the table consists of 5 columns, isn't it? Yes, it is. Yung sa first column, makikita natin dyan is yung mga average number of ships, average waiting time, total ship hours, estimated cost per hour, and etc. Yung 1, 2, 3, 4, yun yung waiting lines. Dito naman sa average number of ships arriving per shift, bakit 5, 5, 5 yung nakalagay dyan? Bakit 5 yung amount? Kasi sabi dun sa problem kanina, it was stated there that approximately 5 ships daw yung arrive to unload their cargoes of steel and ore during every 12-hour work shift. So 5. Yung average waiting time per ship is 7, 4, 3, and 2. Kasi yan yung oras. Kanina, di ba, nasabi yan dun sa problem. Yun, wait. From experience, management estimates that if one team of stevedores is on duty to handle the unloading work, each ship will wait an average of 7 hours to be unloaded. If 2 teams are working, the average waiting time drops to 4 hours. Yung 4 dyan sa 2 teams. And yung for 3 teams, yung sa number 3, it's 3 hours. And yung sa number 4 dyan, which is the 4 teams, meron tayong 2 hours. Okay? So now, proceed tayo dyan sa pangatlo, yung total ship hours lost. If you guys can notice, meron 35, 20, 15, and 10. Paano nga ba yung nakuha sila? Madali lang. It's very simple. Yung average number of ships arriving per shift, let's just multiply it dyan sa average waiting time per ship. Take for example dyan sa first column, yung 5 and 7. Let's just multiply it. 5 multiplied by 7 is equals to 35. And that applies to the rest of the columns here. Dyan sa number 2, 5 times 4 is equals to 20. Third column, 5 times 3 is equals to 15. And fourth column, yung 5 times 2 is equals to 10. Next is yung estimated cost per hour of idle ship time. Bakit 1,000 dyan yung amount? Bakit $1,000? And it was just all constant there. Kasi if you guys really listen to the problem earlier, I stated, naka-mention doon yung amount. Sabi nga, each hour that a ship sits idle in line waiting to be unloaded cost the firm a great deal of money, about $1,000 per hour. Kaya constant dyan yung 1,000 per hour. Now, let's proceed dyan sa pang-apat. Dyan sa next. Sorry, pang-5 pala. Yung value of ships lost time. So, dyan, madali lang din. Let's just multiply yung total ship hours lost and yung estimated cost per hour, yung pang-apat. I-multiply na natin. Take for example, dyan sa first row, yung 35 sa total ship hours lost, i-multiply natin siya sa estimated cost per hour of idle ship time. So 35 multiplied by $1,000 is equals to $35,000, and that also applies to the rest of the columns. Take for example 20, just a second row, 20 i-multiply sa 1,000, it will be $20,000. And yung 15 i-multiply sa $1,000, it will be $15,000. And yung 10 just sa fourth column i-multiply sa $1,000, it would be $10,000. Next, proceed tayo sa stevedore teams. Yung $6,000, $12,000, and $18,000, and $24,000. Paano yun siya nakuha? In multiplying that, yung stevedore team salaries, so these are computed as the number of people in a typical team. So assumed, dito sa problem na to, it was assumed to be 50. Yung 50 times mo lang sa hours each person works per day. So, ilan ba yung hours na pinagtatrabahuan ng isang tao sa isang araw? Diba 12 hours? So, 50 times 12 hours. I-times mo lang din siya ulit dun sa hourly salary ng $10,000 per hour. Kasi diba $10,000 per hour? So, ngayon, 50 i-times mo sa 12 hours times mo sa $10,000 per hour. Yung sagot is 6,000. If you can see dyan sa first column, $6,000 siya. Yan yung sagot. So, if 2 teams are employed, the rate is just doubled. So, it was just all doubled. So, $6,000, $12,000, $18,000, and $24,000. So, ngayon, i-total na natin yung lahat-lahat ng na-compute natin dito. And it's called total expected cost. Now, let's dive in sa total expected cost. Paano yun siya nakuha? Let's just simply find the sum, or let's just all add lahat ng mga amount dito sa first column, second column, third column, and fourth column. Yung 5, 7, $1,000, $35,000, $6,000, and that equals to $41,000. Ngayon, di ba, yan na, total expected cost. Meron tayong $41,000, $32,000, and $33,000, and also the $34,000. Sabi ko nga kanina, di ba, ano yung goal? The goal is to find the service level that minimizes total expected cost. Again, minimizes total expected cost. Ano yung pinaka-minimize dito sa lahat ng total expected cost? Siyempre, yung pangalawang column, kasi yan yung may pinakamababang amount, $32,000. So, yan yung ating total expected cost among this all expected cost ng na-produce natin. Or dito sa problem na ito sa Three Rivers Shipping Company. Okay? Basta tandaan lang talaga natin always na yung goal is to find the service level that minimizes total expected cost. And so that the answer is $32,000. So right now, it's time for us to dive into the characteristics of a queuing system. So, in this focal matter of the characteristics of a queuing system, meron tayong 3 parts or yung tatlong parte ng queuing system. So first, there is yung arrivals or the arrivals or inputs to the systems. So actually, this is sometimes referred to as the calling population. Mamaya i-discuss natin yun siya. Next up is yung queue or the waiting line itself. And yung pangatlo is the service facility. So ngayon, started natin yung arrival characteristics. Dito sa arrival characteristics, meron siyang 3 major characteristics na under dito sa arrival characteristics, we have the 3 major characteristics already. So, ayan nga the input source that generates arrivals or customers for the service system has 3 major characteristics. So, ano-ano yon? Ano yung mga gina-consider ng mga major characteristics? So, syempre, it is vital and beyond crucial na i-consider yung size of the calling population. Ayun. So, also, yung pattern of arrivals at a queuing system. And of course, yung behavior ng ating mga arrivals or the behavior of the arrivals. Okay. So next up is, this table, which is the table 13.1, I already discussed this one earlier, which is the optimal cost. Ayan, mas pinakita lang yung detail nung formula na ginawa ko kanina or discuss ko kanina. Pero ito yung It was all just the same. Okay? So, proceed na tayo sa next page. Next slide. Okay. Okay, so continue. Dito tayo sa arrival characteristics. Okay, yung first na major characteristic niya is yung size of the calling population nga. So, yes, of course, population sizes are considered to be either unlimited or limited. So, yung unlimited, so basically, from the word itself unlimited, it is also referred to us as essentially infinite. And yung limited, which is from the word itself also na limited, it's finite. So, for practical purposes, ano yung mga examples ng ating unlimited population? So, yung examples of unlimited population includes, of course, yung cars arriving at a highway toll booth. Next is yung shoppers arriving at a supermarket. Or yung students arriving to register for classes at large university. Ayan yung ating unlimited or essentially infinite na population. So, paano nga ba natin makonsider yung isang population, whether if it is unlimited or limited? So, when the number of customers or arrivals on hand at any given moment is just a small portion of potential arrivals, syempre, yung calling population natin is undoubtedly considered as unlimited. Okay? So, mostly sa mga queuing models or most queuing models assume such an infinite calling population. Infinite is unlimited calling population. Kasi, if it's not the case, or when this is not the case, modeling becomes much more complex. Okay? So, dito naman tayo sa finite. Ano nga ba yung example? Or ano ba yung mga example? Pero magbibigay ako ng isang example based doon sa ebook or doon sa e-learning na basis natin. So, an example of a finite population is a shop with only 8 machines that might break down and receive service. Okay? So, yan yung ating size of the calling population. So, now, let's proceed sa ating pangalawang characteristic, which is under pa rin sa arrival characteristics. So, ito ay pattern of arrivals at the system. Customers either arrive at service facility according to some known schedule, or else they arrive randomly. So, for example, one patient every 15 minutes or one student for advising every half hour. Arrivals are considered random, of course, when they are independent of one another and their occurrence cannot be predicted exactly. So oftentimes, or should I say frequently, sa ating queuing problems, the number of arrivals per unit of time can be estimated by a probability distribution. So this is known as the Poisson distribution. Sa atin kasing Poisson probability distribution, ginagamit siya in many queuing models to represent what? This is used to represent arrival patterns. So right now, I'll take you a presentation about the Poisson distribution of arrival time. So this is just a glimpse. Since this is not really the focal matter of our topic, I'll just present you the formula and also the illustration. Actually, this is discussed by other groups if you guys listen to the previous reporters. But right now, I'll just present it to you so that you do have an idea what is it all about. So this is the formula of Poisson distribution of arrival. Poisson distribution for arrival time. So this is the formula, which is yung probability of X arrivals and yung number of arrivals per unit of time, average arrival rate, and yung X factorial. So, madali lang to siyang gamitin since we have the rights to use scientific calculator, so you don't have to worry about it. So, right now, let's proceed yung illustration. So, ito yung illustration niya. Okay? Proceed tayo ngayon sa last characteristic ng arrival characteristics, which is yung behavior of the arrivals, no? From the word itself, behavior. It's very understandable and very kind of like eclectic for you to understand what is it all about. But most queuing models assume that an arriving customer is a patient customer. Patient customers are people or machines that wait in the queue until they are served and do not switch between lines. So unfortunately, life and operations research are complicated by the fact that people have been known to balk or renege. Ano ba yung balking and ano ba yung reneging? Yung balking refers to customers who refuse to join the waiting line because it is too long to suit their needs or interests. And your reneging customers are those who enter the queue but then become impatient and leave without completing their transaction. Actually, very, very, very relevant ito siya sa reality. Actually, both of the situations just serve to accentuate the need for queuing theory and waiting line analysis. So, bakit? Hindi ba kayo nakakakita or nakaka-encounter or even yourselves, you don't even encounter this one? Of course, you do. Na-encounter nyo to. Syempre kapag, alimbawa, pumunta kayo ng grocery stores, how many times have you seen a shopper with a basket full of groceries, including perishables such as milk, frozen food, or meats, simply abandon the shopping cart before checking out because the line was too long? Diba? It's beyond, beyond happening in the reality. And it's not even impossible. Even sa mga fast food chain, kapag gutom na gutom ka na, or you have an hectic schedule, you're having a hectic schedule, tapos ang haba ng pila, di ba, you simply leave and just find an alternative where you can eat. Kasi hindi mo naman pwedeng hintayin yung pila na ganun, especially if you're having or if you're dealing with such hectic schedule. That is, this expensive occurrence for the store makes manager acutely aware of the importance of service level decisions. Kaya dito pa lang, it is really vital and crucial for us to understand and to really, really dive in dun sa profoundness kung paano natin i-manage yung service level decisions. So right now, let's proceed. So waiting line characteristics. So in this topic, we will be traversing and learning these two waiting lines characteristics. So we have here the first one, which is the length of the QE, and the next one or the second one, which is the QE discipline or service priority. So yung length of the QE, as just what I've discussed earlier, if you guys listened, the length of a line can be either limited nga or unlimited, which is the limited one, which is the finite, and the unlimited one, which is the infinite. By the way, the waiting line itself is the second component of a queuing system, ha? So, yes, continue tayo. A queue is limited when it cannot, by law of physical restrictions, increase to an infinite length. So this may be the case in a small restaurant that has only 10 tables and can serve no more than 50 diners an evening. So, analytic queuing models are treated in this chapter under an assumption of unlimited queue length. Okay? So, yung queue, it's limited when its size is unrestricted, as in the case of the toll booth serving arriving automobiles. Ngayon, proceed tayo dun sa second waiting line characteristics. A second waiting line characteristics deals with queue discipline. To queue discipline, we should also refer this one as service priority. So queue discipline refers to the rule by which customers in the line are to receive service. So mostly guys, ang systems dito, it uses a queue discipline known as the first in, first out, or yung FIFO rule, which I mentioned earlier dun sa first topic natin. Dun sa first chapter ng topic natin. So, magbigay tayo ng example, in a hospital emergency room or an express checkout line at a supermarket. However, various assigned priorities may preempt FIFO. So patients who are critically injured will move ahead in treatment priority over patients with broken fingers or noses. Isa pa. Shoppers with fewer than 10 items may be allowed to enter the express checkout QE, but are then treated as the first come, first served first come, first served, sorry. So computer programming runs are another example of queuing systems that operate under priority scheduling. So in most large companies, when computer produced paychecks or are due out on a specific date, the payroll program has highest priority over other runs. So ano pa yung mga ibang customers, ay ibang mga disciplines na customers may be served according to the one of the next disciplines here. So yung first in first out or yung FIFO na rule, just like what I've mentioned earlier, and yung priority discipline and last come first served, which I already discussed it earlier, and also the service and random order. Ngayon, proceed tayo sa service facility characteristics, which is the third part of any queuing system. So this is called service facility. By the way, it is important to examine two basic properties here. The first basic property here is the configuration of the service system, and the second one, which is the pattern of service times. Okay? So simulan natin dito sa basic queuing configuration. So service systems are usually classified in terms of number of channels and also the number of phases in service. So sa number of channels, meron tayong tinatawag niya a single channel system. So with one server, it is typified by the drive and bank that has only one open teller. And doon naman sa multi-channel system, when the bank has several tellers on duty and each customer waits in one common line for the first available teller. Mamaya magpapakita tayo ng illustrations with regards to this systems para hindi kayo ganun ka mag-overthink when it comes to like that one. Okay? So i-add ko lang din na sa single channel system, yung pinaka-basic or most prominent example of this one would actually be the drive-thru of every fast food chains that we have here in the city. Yung mga drive-thru dyan, single channel system yan sila. And sa multi-channel system naman, is probably yung mga banks today, they are using multi-channel service systems. They're mostly yung mga large barbershops din and many airline ticket counters. Okay? Yan yung mga examples or prominent examples of multi-channel system. So right now, proceed naman tayo dun sa number of phases and service, which is under pa rin sa service facility characteristics. So kung yung kanina is channels yung pinag-uusapan, ngayon naman is yung phases in such services. So first up here, we have the single phase system. So in this case, the consumers or the customers receives service from only one station and then exits the system. Okay, so let's try to elongate the discussion by giving you guys a bunch of examples. Really a prominent example of this one would probably the fast food restaurant, I guess. And again, so in which the person who takes your order also brings you the food and takes your money is already considered as a single phase system. So is a driver's license agency, in which the person taking your application also your grades, your test, and collects the license fee. That's also considered as single phase system. And okay, however, if the restaurant or if that fast food requires you to place your order at one station, pay at a second and pick up the food at a third service stop, it becomes, or it'll be a multi-phase system. Actually, to multi-phase system, ang pinakaalam ko na example na um, very, I think it's very modern or kind of like popular or lahat tayo nakakaalam, siguro yung ating university canteen here sa campus or dito sa institution natin, dito sa Notre Dame University. Yung ating university canteen is actually a multi-phase system kasi iba yung process ng payment, pag-order, and also yung pag-claim mo ng food. So, that's a multi-phase system. Sorry. Okay, so, to help you relate the concepts of channels and phases, meron tayo ditong mga, just like what I've said earlier, meron tayong mga illustrations here. Okay? So, first, ito. As you can see in the presentation, yung arrivals, yung single channel or single phase system. So, syempre, from the word itself, yung single channel or single phase, so it's just a single system all over up there. So, yes, yung arrivals ng ating customer, pagpasok nila is pipila sila for the service facility and then they could have the, the gratification that they are demanding. And also, here's a single channel but multi-phase system. Syempre, single channel siya, but it has multi-phase system. Just like what I've said earlier, pinaka-great example of this one would probably our university canteen here. Within here, this is the institution of NDU, which is the Notre Dame University. Because it has arrivals, and pag pumila sila, they will be traversing might be 2 or 3 processes of service facility, which is yung pagbayad, pag-claim, and pag-order ng food. Sorry, pag-order, pagbayad, at pag-claim ng food. So, next is yung multi-channel or single-phase system. So, ayan. Marami siyang channels, but it has only single-phase system. Pag-arrive mo, we have here the 3 service facility. Okay? Which is the departures, the after, and also yung service. Next is yung multi-channel or multi-phase system. So, most probably it has all multi-sections there. Pagpasok mo, you will be encountering a multi-channel and also the multi-phase system. And that would be quite, I think that's kind of stressing for us kasi sometimes if we do have something in needs that really, kind of like nagmamadali tayo. So this kind of system or channel would probably, or this kind of service facility in general would kind of be grounded or sort of like complicated in our schedule or in our routine. Okay. So next up is yung pattern service times, which is underpinning sa service facility characteristics. So, service patterns are like arrival patterns in that they can be either constant or random. So, if service time now is constant, it takes the amount of time to take care of each customer. So, this is the case in a machine-performed service operation such as an automatic car wash. Diba? If mapapansin niyo, yung service doon is constant and it takes amount of time to take care of each customer. Since kailangan ng investment when it comes to like the time sa paghugas, pagwash ng every cars there, which is automatically naman siya. More often, service times are randomly distributed. So in many cases, it can be assumed that random service times are described by the negative exponential probability distribution. So the exponential distribution is really that vital. So it's really important talaga to the process of building mathematical queuing models. Kasi nga, many of the models, the theoretical underpinnings are based on the assumption of Poisson arrivals and exponential services. So before they are applied, however, the quantitative analyst can and should observe, collect, and plot service time to determine if they fit the exponential distribution. So take note lang. Take note lang po tayo guys here. It is really that important and really that vital and crucial to confirm that the queuing assumptions of Poisson arrivals and exponential services are that valid before applying the model. Okay? So here is the next figure, which illustrates that if service time follows, if that service times follows an exponential distribution, the probability of any very long service time is also low. So right now, let's dive in and just briefly discuss this identifying models using candle notation. So as we can see here, we have DG Kendall or David George Kendall. So he developed a notation that has been widely accepted for specifying the pattern of arrivals, the service time distribution, and also the number of channels in a queuing model. So the three basic symbol Kendall notation is in the form of what? In the form of arrival distribution, service time distribution, and also that number of service channels open. So where specific letters are used to represent probability distributions, the following letters are commonly used in Kendall notation. So ano-ano yung mga letters na yon? We have here the M, D, and G. So M, which is the Poisson distribution for number of occurrences or exponential times, and yung D, which is the constant or deterministic rate, and yung G, which is the general distribution with theme and variance known. So now let's proceed. So a single channel model with Poisson arrivals and exponential service times would be represented by M-M-1. So when a second channel is added, we would have M-M-2. Okay, so if there are M distinct service channels in a queuing system with Poisson arrivals and exponential service, the Kendall notation would be M-M-M. So ngayon, a three-channel system with Poisson arrivals and constant service time would be identified as M-D-3. So kung four-channel system naman with Poisson arrivals and service times, these are normally distributed as or identified as M-G-4. So take note, an M-M-2 model has Poisson arrivals, exponential service times, and two channels. Okay. A three-channel with Poisson arrivals and constant service time would be, yes, it's just what I've discussed earlier, M-D-3. And also a four-channel system with Poisson arrivals and service times that are normally distributed would be identified as M-G-4. So there is a more detailed notation with additional terms that indicate the maximum number in the system and the population size. So when these are omitted, it is also assumed na there is no limited to the QE length or the population size itself. So most of the models we study here will have those properties. So ngayon, let's proceed doon sa next topic, which will be covered by the next reporter. Thank you.
Next topic is all about a single channel queuing model with Poisson arrivals and exponential service times. So what are the assumptions of this model? The single channel, single phase model considered here is one of the most widely used and simplest queuing models. It involves assuming that these 7 conditions exist. First, arrivals are served on a FIFO basis. So ano nga ba yung FIFO basis natin? It means first in and first out. Sa loob ng company, ang first na mabibili nilang produkto ay ang siyang una ding lalabas. From the word itself, first in will be its first out. Second, every arrival waits to be served regardless of the length of the line, that is, there is no balking or reneging. Third, arrivals are independent of preceding arrivals, but the average number of arrivals or the arrival rate does not change over time. Fourth, arrivals are described by a Poisson probability distribution and come from an infinite or very large population. Fifth, service times also vary from one customer to the next and are independent of one another, but their average rate is known. Sixth, service times occur according to the negative exponential probability distribution. Seventh, the average service rate is greater than the average arrival rate. When these 7 conditions are met, we can develop a series of equations that define the queue's operating characteristics. So, what are the performance measures of queuing system? So, we have 7 performance measures. These are average time each customer spends in the queue, average length of the queue, average time each customer spends in the system, average number of customers in the system, probability that the service facility will be idle, utilization factor for the system, and last, probability of a specific number of customers in the system. So these 7 performance measures have its own formula. So next we have queuing equation. We let lambda means number of arrivals per time period and Q means number of people or items served per time period. When determining the arrival rate and the service rate, the same time period must be used. So, ito yung magagamit nating variables in solving all the performance measures in the model. So, as you can see in the slide, this will be the queuing equations that will be used in solving queuing models. So, for number 1, we have the average number of customers or units in the system. L, that is the number in line plus the number being served. So, the formula would be like this. L is equal to arrival rate divided by service rate minus arrival rate. So second, the average number a customer spends in the system, W, that is the time spent in the line plus the time spent being served. So W is equal to 1 divided by service rate minus arrival rate. So the number 1 here is constant. Third, the average number of customers in the queue. LQ is equal to arrival rate to the power of 2 divided by service rate times service rate minus arrival rate. Number 4. The average time a customer spends waiting in the queue, or WQ, is equal to arrival rate divided by service rate times service rate minus arrival rate. Fifth, the utilization factor for the system, or P, the Greek lowercase letter rho, that is the probability that the service facility is being used. So the formula would be P is equal to arrival rate divided by service rate. Sixth, the percent idle time, or P sub 0, that is the probability that no one is in the system. So the formula would be P sub 0 is equal to 1 minus arrival rate divided by service rate. Seventh, the probability that the number of customers in the system is greater than K. So the formula would be P sub n is greater than K is equal to arrival rate divided by service rate to the power of K plus 1. So we have Arnold's mufflers shop case. Arnold's mechanic, Reed Blank, is able to install new mufflers at an average rate of 3 per hour, or about 1 every 20 minutes. Customers needing this service arrive at the shop on the average of 2 per hour. Larry Arnold, the shop owner, feels that all 7 of the conditions for a single-channel model are met. He proceeds to calculate the performance measures of the system. So our given would be 2 cars arriving per hour, which is our arrival rate, and 3 cars service per hour, which is our service rate. So we have our solution here. First, we are going to solve the average number of customers or units in the system. So we just need to substitute all the given value to the variables and we will come up to its answer. So L is equal to 2 divided by 3 minus 2 would be 2 all over 1, or 2 in simplified form. We have 2 cars in the system on the average. Second, in solving the average car spends in the system, we will have W is equals to 1 divided by 3 minus 2. We will come up with an answer of 1 hour that an average car spends in the system. Third, we are going to solve the average number of customers in the queue. Then that will be LQ is equal to 2 to the power of 2 divided by 3 times 3 minus 2. and we'll come up with an answer 1.33 cars waiting in line on the average or 1 car waiting on the line average. Kasi hindi natin siya pwede i-round off. Walang 0.33 cars and hindi rin natin siya pwede gawing or i-consider na isa pang car ulit. So, fourth, we're going to solve the average time a customer spends waiting on the queue. So, WQ is equal to 2 divided by 3 times 3 minus 2, and that will be 2/3 hour or 40 minutes average waiting time per car. So, note that W and WQ are in hours. Since arrival rate was defined as the number of arrivals per hour, so sabi dito, we need to change our unit into hours kasi yun yung given sa problem natin. So, we just need to solve the utilization factor, which is P is equal to 2 divided by 3, and that would be 0.67 or 67% of time mechanic is busy or the probability that the server is busy. So, next, we will solve the probability that there is no one in the system, and that will be P sub 0 is equal to 1 minus 2/3, and we will come up with an answer of 0.33 or 33% probability that there are 0 cars in the system. So, next, hahanapin natin yung probability of more than K cars in the system. So, here, nagkaroon siya ng trial and error to find the closest percentage and numbers of cars dun sa given value natin. So, as you can see, 0.198 is yung percentage natin sa 3 cars. So, next, we are going to solve for the probability of more than K cars in the system. So, dito sa slide na to, nagpakita siya ng trial and error to check the probability na merong more than 3 cars in the system. Pero, if gusto natin ng mas madali, we just need to substitute all the variables sa given formula, which is yung P sub N is greater than K. So, to calculate that, we just need to substitute, then the outcome will be 0.198. So, this implies that there is a 9.8% chance that more than 3 cars are in the system. So, yun na yung magiging final answers natin. So, next, this shows the XLQM solution to Arnold's muffler example. So, actually, na-solve na natin to siya kanina. And, pinakita lang dito ano ba yung itsura niya once nag-input tayo ng mga ganong information sa XLQM. Next, introducing cost into the model. As stated earlier, the solution to queuing problem may require management to make trade-off between the increased cost of providing better service and the decreased waiting cost derived from providing that service. These two costs are called the waiting cost and the service cost. So, ang formula natin for total service cost would be total service cost is equal to number of channels times cost per channel. Or in short, total service cost is equal to MCS. So, M means number of channels, CS means service cost or labor cost of each channel. The waiting cost when the waiting time cost is based on the time in the system, which is total waiting cost is equal to total time spent waiting by all arrivals times cost of waiting. So, a simplified formula would be total waiting cost is equal to W times CW. If waiting time cost is based on the time in the queue, this becomes total waiting cost is equal to WQ times CW. So, for the formula, for the total cost of the queuing system, total cost is equal to total service cost plus total waiting cost. So, pwede ito siyang i-derive into two formulas, which are total cost is equal to MCS plus W times CW, or total cost is equal to MCS plus WQ times CW. So, after discussing all the formulas, sasagot na naman tayo ng another problem na pwede natin i-imply yung mga formulang yon. So, Arnold estimates that the cost of customer waiting time in terms of customer dissatisfaction and lost goodwill is $10 per hour of time spent waiting in line. Because on the average, a car has a 2/3 hour wait and there are approximately 16 car service per day, 2 per hour times 8 working hours per day, the total number of hours that the customer spend waiting for mufflers to be installed each day is 2/3 times 16 which will be 32 hours. Hence, in this case, the total waiting cost will be 8 hours per day, and the WQCW would be 8 times 2 times 2/3 times $10 would be $106.67. So, another example, what if the only other cost that Larry Arnold can identify in this queuing situation is the pay rate of Reed Blank? The mechanic Blank is paid $7 per hour. So, to solve this, total daily service cost is equal to 8 hours per day, and the NCS would be 8 times 1 times $7 would be $56. The total daily cost of the system as it currently configured is the total of the waiting cost and the service cost, which gives us total daily cost of the queuing system is equal to $56 or $162.67. So, paano tayo nag-come up dun sa 162.67? Tulad sa sabi ko kanina, yung total daily waiting cost natin na 106.67, i-add natin yun siya dun sa result ngayon na total service cost na 56. So, ipa-plus natin, we will come up with the answer 162.67. So, another example would be Arnold's muffler shop case. Now comes a decision. Arnold finds out through the muffler business grapevine that the Rusty Muffler, a cross-down competitor, employs a mechanic named who can efficiently install new mufflers at the rate of $4 per hour. Larry Arnold contacts Smith and inquires as to his interest in switching employers. Smith says that he would consider leaving the Rusty Muffler, but only if he were paid a $9 per hour salary. Arnold, being a crafty businessman, decides that it may be worthwhile to fire Blank and replace him with the speedier but more expensive Smith. He first recomputes all the operating characteristics using new service rate of 4 mufflers per hour. So in this sample, nagbago na yung value ng mga variables natin na arrival rate and service rate. Yung arrival rate natin naging 2 cars arriving per hour, which is hindi nagbago. And ang nagbago sa atin is yung service rate kasi nga papalitan ni Smith si Blank, which will be the service rate na 4 cars service per hour. So again, tulad ng ginawa natin kanina sa pinakaunang sample natin, we just need to substitute and perform all the 7 formulas na ni-require sa single channel model natin. So, to find the average car in the system, L is equal to 2 divided by 4 minus 2 would be 1 car in the system on the average. Second, to find the system on the average, W is equal to 1 divided by 4 minus 2 and magka-come up tayo sa 1/2 hour. Next, LQ is equal to 2 to the power of 2 divided by 4 times 4 minus 2 and magka-come up naman tayo sa 1/2 cars waiting in the line on the average. Fourth, WQ is equal to 2 divided by 4 times 4 minus 2 is equal to 2/8 or 1/4 in simplified form. And if in minutes na units, magka-come up tayo sa 15 minutes average waiting time per car in the queue. To solve the utilization factor, P is equal to 2 divided by 4 and that would be 50% of the time mechanic is busy. And probability that the system is empty would be P sub 0 is equal to 1 minus 0.5 and that would be 50% probability that there are 0 cars in the system. So next, tulad kanina, nag-trial and error siya kung sino ang pinakamalapit na value and percentage dun sa given na numbers ng car. It is quite evident that Smith's speed will result in considerably shorter queues and waiting times. For example, a customer would now spend an average of 1/2 hours in the system and 1/4 hour waiting in the queue, as opposed to 1 hour in the system and 2/3 hour in the queue with Blank as mechanic. The total daily waiting time cost with Smith as the mechanic will be total daily waiting cost is equal to 8 hours per day times arrival rate times WQ times CW. So after substituting all the value on the given variables or formula, we will come up with a $200 per day. Notice that the total time spent waiting for the 16 customers per day is now 16 cars per day times 1/4 hour per car would be 4 hours, instead of 10.67 hours with blank. Thus, the waiting is much less than half of what it was, even though the service rate only changed from 3 per hour to 4 per hour. The service cost will go up due to the higher salary, but the overall cost will decrease. As we see here, service cost of Smith would be 8 hours per day times $20 per hour would be $160 per day. The total expected cost is equal to waiting cost plus service cost is equal to 200 plus $160, and that will be $360 per day. Because the total daily expected cost with blank as mechanic was $653.33, Arnold may very well decide to hire Smith and reduce costs by $653.33 minus $360 is equal to $293.33 per day. So, in conclusion, na-compare niya dito yung value na mababayad niya kay blank and yung value na mabayad niya kay Smith. So, dahil nga mas mabilis si Smith, though mahal siya, magka-come up rin siya sa mas murang salary if ibibigay niya yun kay Smith. Compared mo kay Blank na matagal na nga yung process ng service time and mahal pa yung salary. So, ano bang mas pipiliin ni Arnold? So, yun ang final decision making niya. If i-consider niya ba si Smith as his mechanic kasi mas maganda ang service, though mahal ang salary, or si Blank na mabagal ang service kaysa kay Smith, pero mahal din ang salary. So, that will be the question at the end of the day by Sir Arnold. So, that would be all for single channel model.
3-5 Multi-channel queuing model with Poisson arrival and exponential service time. What is multi-channel queuing model with Poisson arrival and exponential service time? This is a case 2 or more servers are available to handle arriving customers. Each one of stations can deliver the same type of service and equipped with same time of facilities. Their service is first come first serve, and all servers are assumed to perform at the same rate. In the next slide is the equation for the multi-channel queuing model. So the equation for number of channel open, the equation of average arrival rate, and the equation for the average service rate at each channel. The next slide is the formula may be used in waiting line analysis number 3, the average time a unit spends in the waiting line or being serviced. The next slide is Arnold's muffler shop example. Suppose that Arnold opened a second garage bay in which mufflers can be installed. Instead of firing his first mechanic, he would hire a second worker. The new mechanic will be expected to install mufflers at the same rate as about 3 per hour. Customers who would still arrive at the same rate of 2 per hour would wait in a single line until one of 2 mechanics is free. To find out how this option compares with the old single-channel waiting line system, Arnold computes several operating characteristics for the two-channel system. To complete his economic analysis, Arnold assumes the second mechanic would be paid the same as the current one, namely $7 per hour. The total daily waiting cost is 8 hours. To get the sum, multiply the 8 by 2 by 0.0415 by $50 and the total daily waiting cost will be $33.20. Next is total daily service cost. To get the sum, multiply the 8 by 2 by $15 and the total is $240. The total daily waiting cost is $33.20 and the total daily service cost is $240. So you should add the $240 and $33.20 and that is equals to $273.20 and that is the total cost of queuing system. In the next slide is effect of service level on Arnold operating characteristic. The following level of service operating characteristic: 1 mechanic, 2 mechanic, 1 fast mechanic. Probability that the system is empty: the 1 mechanic is 0.33, the 2 mechanic is 0.50, the fast mechanic is 0.50. Average number of cars in the system: the 1 mechanic is 2 cars, the 2 mechanic is 0.75 car, the fast mechanic is 1 car. Average time in the system: that 1 mechanic is 60 minutes, the 2 mechanic is 22.5 minutes, the fast mechanics is 30 minutes. Average number of the QE: the 1 mechanic is 1.33, the 2 mechanic is 0.083, the fast mechanic is 0.50 car. Average time in the QE: the 1 mechanic is 40 minutes, the 2 mechanic is 2.5 minutes, the fast mechanic is 15 minutes. In the last slide is the Excel QM. So using the Excel QM, this is the solution or the steps to solve the problem in Excel QM.
Good day everyone, I am Shahani Alsama, and for our next topic, we are going to discuss about constant service time model. So what is constant service time model? Some service systems have constant service times instead of exponentially distributed times. When customers or equipment are processed according to a fixed cycle, as in the case of an automatic car wash, constant service rates are appropriate. Because constant rates are certain, the values for average length of the queue, average waiting time in the queue, average number of customers in the system, and lastly, average time in the system are always less than they would be in the models we have just discussed, which have variable service times like Poisson distribution, exponentially distribution services. So, pag sinabi natin constant service time model, from the word itself, constant siya. We are going to use formulas which are called steady-state formulas. So, ano nga ba yung mga steady-state formulas? Ang steady-state formulas ay mga formulas na hindi natin pwede palitan. Hindi pwede natin i-derive, hindi natin pwede gawan ng another formula from the original formula kasi that would result to wrong answers. Hindi natin makukuha yung hinahanap natin na sagot sa mga problem na tinatry nating sagutan. And also, ang mga steady-state formulas or yung mga formulas na gagamitin natin dito sa constant service time model ay hindi natin pwedeng i-trial and error. Maliban kung humahanap siya ng confidence level, kasi once kasi na naghahanap tayo ng confidence level, we are aiming for the closest number on the given problem. So, mag-try tayo ng different percentage para lang mag-come up dun sa confidence level na hinahanap natin. Dun lang siya pwede i-imply, but on other formulas, hindi tayo pwede mag-trial and error. In the next slide, as you can see, these are the formulas being used or equations being used in a constant service time model. So first, the formula for the average length of the queue. Second, average waiting time in the queue. Third, average number of customers in the system. And fourth, average time in the system. So, now, we are going to try to use all those formulas in the given problem. So, Garcia Golding Recycle Incorporated collects and compacts aluminum cans and glass bottles in New York City. Its truck drivers who arrive to unload these materials for recycling currently wait an average of 15 minutes before emptying their loads. The cost of the driver and truck time waste while in queue is valued at $60 per hour. A new automated compactor can be purchased that will process truckloads at a constant rate of 12 trucks per hour. Trucks arrive according to a Poisson distribution at an average rate of 8 per hour. If the new compactor is put in use, its cost will be amortized at a rate of $3 per truck unloaded. A summer intern from a local college did the following analysis to evaluate the cost versus benefits of the purchase. So next, we are going to use all the formulas that I have stated a while ago in this problem. So this is the Excel QM solution for constant service time model with Garcia Golding Recycling. So you must be confused paano tayo nagka-ama up sa mga ganyang results. So let me show you how to solve it in a manual way. First and foremost, we are going to follow the flow of the formula. So kung ano yung unang formula naka-state dun sa slide before, yun yung una-una nating is-solve. But before that, it is considered na ang hahanapin natin in the first place is yung average server utilization or yung P. So, paano ba natin makukuha yung value ng P? So, to solve the average server utilization or the value of P, the formula would be P is equal to arrival rate divided by service rate. So, based on the given problem, ang value natin ng arrival rate is 8 and ang service rate is 12. So, we're going to substitute the given value sa mismong formula. So, 8 divided by 12 is equal to 0.6666 bar kasi repetition or 0.666667. Pwede natin siyang i-round off. So, ito yung magiging sagot natin for the average server utilization. So, as you can see in the Excel QM, we have same answers. Ito yung paraan para ma-solve natin siya manually. If ever wala tayong Excel QM or wala tayong laptop, we can solve it manually. So next, ang hinahanap naman natin is ang average number of customers in the queue. So after solving the average server utilization or P, we are going to solve the average number of customers in the queue. So the formula would be LQ is equal to arrival rate to the power of 2 divided by 2 times service rate, open parenthesis, service rate minus arrival rate. So, same pa rin tayo sa given natin dito. Bali, we are going to substitute again. Bali, 8 to the power of 2 divided by 2 times 12, open parenthesis, 12 minus 8, close parenthesis. So, if you have your scientific calculator, you can input this. Pero, if magmano-mano, pwede kayong mag-come up sa ganito. So, we should follow the rule of PEMDAS. Unahin natin ang parenthesis. So, 12 minus 8 would be 4. And 2 times 12 is 24. Next is exponent. So, 8 times 8, kasi nga 2 dito, bali 64. So, perform the operation first. Bali 24 times 4 would be 96. And 64 naman ang numerator natin. So, to solve that, pwede tayong gumamit ng basic cal, pwede din scientific calculator. Bali, 64 divided by 96, magka-come up tayo sa 2/3 or 0.6667. Same pa din sa number 1 na sagot, pero iba nga lang din ang hinahanap, nagkataon lang na same ang answers. Bali, i-compare natin to siya sa sagot sa Excel QM. Bali, as you can see, same siya. Bali, tama ang ginawa nating process. So, next, we are going to solve the average number of customers in the system. So, ito yung third formula na sasagutan natin. Bali, the formula for number 3 is LS is equal to LQ plus arrival rate divided by service rate. So, always nating tandaan na ang mga waiting line and queuing models ay may sunod-sunod na process na sinusunod. Kasi if ever wala kang sagot dito, hindi mo masasagutan to kasi kasali ang LQ sa problem ng LS. Bali, isa-substitute lang natin So, ang LQ natin is 0.66667 plus arrival rate natin na 8 and service rate natin na 12. So, if you have your calcu, solve natin yan. Bale, 0.66667 plus 8 divided by 12 is equal to 1.3333667. 0.3333 bar na. Hindi natin siya ma-round off. Bali, ito na ang magiging sagot natin. If wala tayong cycle, pwede namang ganito, 0.667 tapos, i-plus natin sa 8 divided by 12. Same pa din ang result. So, ayan. Basta we need to follow the PEMDAS para hindi tayo magkamali ng sagot at the end. So, next is the average waiting time in the queue or WQ. Okay, solve natin siya dito. For number 4, ang formula sa WQ is arrival rate divided by 2 times service rate, open parenthesis, service rate minus arrival rate. So, again, substitute ulit. 8 divided by 2 times 12, open parenthesis, 12 minus 8. So, input natin siya sa calcu. If may cycle kayo, good for you kasi masosolve natin siya agad-agad. Times 12. 12 minus 8 equals 1 out of 12. So, ang magiging sagot natin is 0.083333 bar. Hindi rin natin siya ma-round off, kaya yan na ang ating answer. So, again, compare natin siya sa Excel QM na nasa slide before. Same ang sagot, bale, same din ang process natin. Kahit mag-solve tayo ng manual, same pa din ang sagot. Bali, for number 5 or 5th formula na susundin natin is ang average time in the system, WS. So, anong formula for WS? WS is equal to WQ plus 1 divided by service rate. So, yung 1 dito, constant na siya. So, again, let me remind you na without answering this WQ, we will not come up with the answer WS. So, i-perform natin yung operation. 0.08333 plus 1 divided by 12. Bali, check natin sa calcu. 0.083333 plus 1/12. Meron tayong 0.16666 on ground. Pag i-round off natin, meron tayong 0.1666667. So, based sa Excel QM, tama rin ang sagot natin. So, ayan. So, for number 6, ang ginahanap natin is wala natin na state sa constant service time model na formula. Ang hinahanap naman natin dito is probability or percentage of time system is empty. So, ano nga ba yung formula natin dito? If nakinig kayo sa previous reporters, na-state na nila doon yung formula for probability. Bali, ito yung formula na susundin natin. 1 minus arrival rate divided by service rate. So, substitute again. 8 divided by 12. Pwede natin ito siyang i-decimal, pero mas mahirap siya for us. Mas maganda, i-diretso na lang natin. So, 1 minus 8 divided by 12 is equal to 1/3 or 0.333. Again, hindi natin siya pwede i-round off. kasi nga hindi siya umabot ng 5. So, ito yung probability. Kapag hiningi natin sa final answer is percentage, ang magiging sagot natin is 33.33%. So, ayan. After answering all these problems, as you can see, same ito sa Excel QM natin na solution. But, Excel QM, meron na siyang input formula. So, mas madali doon. Pero, if we are solving manually, if pinapasugot tayo sa exams, sa quizzes, we could follow this one. So, after solving all the formulas, para mag-come up tayo dun sa mga answers na nakita natin sa Excel QM solution, meron pa tayong isa pang need i-consider. It is stated here na if the new compactor is put in use, its cost will be amortized at a rate of $3 per truck unloaded. Bali, from that sentence, sabi niya nagkaroon daw ng amortization ng $3 per truck. So, paano natin isosolve yun? So, as you can see in this slide, andito na yung solution and I will going to explain to you paano natin masosolve yun dahil dun sa amortization na $3 per truck. So first, we are going to solve for the current waiting cost per trip. So, sabi dun kanina, 15 minutes ang pag-unload ng isang truck. So, dahil nga gagamitin natin yung hour na unit, i-convert natin yung 15 minutes na pag-unload ng truck into hours. Bali, 1/4 yun siya. I suggest to use fraction kasi merong mga decimal na nagkakaroon ng bar or repetition of numbers. So, bale, ngayon, gagamitin natin yung 1/4 kasi yun yung value or yung unit ng 15 minutes in hours. So, ita-times natin yung 1/4 hour waiting now times $60 per hour cost. Ito rin nakastate, ito siya kanina na $60 daw ang cost per hour sa pag-unload ng truck. Bali, ang current waiting cost natin per trip would be $15 kasi 1/4 times $60 would be $15. So, eto siya, etong average waiting time in queue, na-solve na natin to siya actually kanina. Pero, gilagay lang natin to siya dito kasi it is included para ma-solve natin yung changes na nagkaroon dahil dun sa amortization rate. Bali, kanina nga, nag-come up tayo sa 0.08333 bar sa average waiting time in queue. Pero pag fraction nga ang susundin natin, bali 1/12 hour lang yun siya. So, to solve the waiting cost per trip with the new compactor, so eto siya, new na siya, gagamitin natin yung 1/12 hour times $60 per hour cost. Bali, magka-come up tayo sa $5 per trip. So, next, we are going to solve the savings with new equipment. Etong savings with new equipment is to solve natin para ma-determine natin ilan yung savings natin before and after ng changes na nangyari. So, yung kanina, meron tayong $15, which is yung current system. Yun na yung 15 minutes ang ma-occupy niya. Then, ima-minus natin siya dun sa $5, which is yung new system, na 1/12 hour ang na-consume naman. Bale, we will come up with the answer, $10 per trip. Yun yung sagot natin sa savings with new equipment. Pero, di pa dyan nagtatapos. Need natin ma-apply yung $3 amortization na nasabi dun sa problem. Bali, ang gagawin natin, ima-minus natin yung cost of new equipment amortized, which is yung $3 sa savings with new equipment, which is $10. Bali, 10 minus $3 is equal to $7. So, yung $7 na yun na yung net savings natin. So, always remember all the formulas that have been discussed in our report para to avoid errors din at the end. After the constant service time model, we are going to proceed to the finite population model. What is finite population model? When there is a limited population of potential customers for a service facility, we need to consider a different queuing model. The limited population model permits any number of servers to be considered. The reason this model differs from the 3 earlier queuing models is that there is now a dependent relationship between the length of the queue and the arrival rate. To illustrate the extreme situation, if your factory had 5 machines and all were broken and awaiting repair, the arrival rate would drop to 0. In general, as the waiting line becomes longer in the limited population model, the arrival rate of customers or machines drops lower. So in this case, we will describe a finite calling population model that has the following assumption. There is only one server, the population of units seeking service is finite, arrival follows a Poisson distribution, and service times are exponentially distributed, and customers are served on a first-come, first-served basis. From the word itself, finite, it means limited lang yung tatanggaping customers sa isang server. So, these are the equation for the finite population model. Lambda means arrival rate, and Q is equal to service rate. So, here are the equations for the finite population model. Lambda means arrival rate, Q means service rate, N is for size of the population. The operating characteristics for the finite population model with a single channel or server on duty are as follows. So, meron tayong 6 na formula dito. So, we have a probability that the system is empty, average length of the queue, average number of customers or units in the system, average waiting time in the queue, average time in the system, probability of n units in the system. So, as you can see, medyo mas complicated na yung formula natin compared sa constant service model. And yung mga average length of the queue, average number of the customers, yung mga formula na yon ay nagkaroon din ng changes sa formula. Pero, same pa din ang gagawin natin. We just need to substitute all the given value to these variables or to this formula. So, next, we are going to apply all the formulas that I have stated in this problem. So, the Department of Commerce past records indicate that each of the 5 high-speed page printers at the U.S. Department of Commerce in Washington, D.C. needs a repair after about 20 hours of use. Breakdowns have been determined to be a Poisson distributed. The one technician on duty can service a printer in an average of 2 hours, following an exponential distribution. So, to compute the system operation characteristic, we first note that the mean arrival rate is 1 out of 20 or 0.05 printer per hour. The mean service rate is, so bakit nga ba ang value ng arrival rate natin at ang service rate natin ay fraction? Kasi, we need to determine ilan ang capacity per hour.
Ilang printer ang masisira, ilang printer ang maayos sa certain time. Bali, sa arrival rate natin, meron tayong 1 out of 20 kasi isa yung nasira within 20 hours. And meron naman tayong 1/2 na service rate kasi isa ang maayos within 2 hours.
So first, ang hinahanap natin is the probability that the system is empty. So dito, medyo complicated yung formula and pwede mo siya i-solve manually pero ang haba ng procedure kasi need mo siya ita-times ng paulit-ulit. But here, we are going to show you paano mas mapadali yung pag-solve natin dito. So, I suggest is uunahin natin yung denominator kasi I've tried to answer it with the numerator. Kung i-perform natin yung numerator, hindi tumutugma yung answer. So, itatry natin i-solve ito. Unahin natin ang denominator muna. Now, tuturuan ko kayo paano ilagay yung symbol ng sum. So, we just need to click the shift and hanapin yung symbol ng sum. As you can see, ayan siya. Bali, shift is equal to, then lalabas yan, then you just need to put the value. Next, ang tuturo ko naman kay how to put factorial sa cycle nyo. If tinatamad kayong magmano-mano, we just need to click shift and hanapin yung may sign ng factorial. Bali, shift is equal to, yan, lalabas na siya. After that, perform the operation and substitute same sa nakikita nyo sa slide na ito, then magka-come up kayo sa 0.564. And if you want yung mano-mano, if ever wala kayong cycle, ito yung pwede nyong gawin. Then, after that, yung result na ito, i-divide nyo siya sa 1. And magka-come up pa rin kayo sa 0.564. So, next is the average length of the queue. So, yon substitute lang din natin. Bali, 5 minus 0.05 plus 0.5 divided by 0.05 times 1 minus probability that the system is empty is equal to 0.2 printer. So, yon, need natin muna makuha yung probability na system is empty kasi require yun siya sa formula ng average length of the queue. So, third one is the average number of customers or units in the system. So, the formula would be L is equal to LQ plus 1 minus the probability that the system is empty. So, substitute, bale, ang LQ natin is 0.2 plus 1 which is constant minus 0.564 which is yung probability natin na yung system ay empty. Then, magka-come up tayo sa 0.64 printer. So, pwede dito na ang magiging kinalabasan is number of customers, pwede rin number of units. Depende sa given problem yan. So, next, to solve the average waiting time in the queue, the formula would be WQ is equal to LQ divided by N minus LS times arrival rate. So, substitute again, 0.2 divided by 5 minus 0.64 which is yung value ng LS natin from the third formula. Then, ita-times natin siya sa arrival rate natin na 0.05. Then, magka-come up tayo sa 0.91 hours. Then, next, after natin makuha yung average waiting time in the queue, hanapin naman natin yung average time in the system. Bali, ang formula natin would be WS is equal to WQ plus 1 divided by service rate. So, substitute ulit, 0.91 plus 1 divided by 0.50 is equal to 2.91 hours. So ayun, we already solved the formula from 1 up to 5, but meron siyang dinagdag na assumption or like additional changes. Sabi dito na ang Department of Commerce, if printer downtime costs $120 per hour and if printer downtime costs $120 per hour and the technician is paid $25 per hour, hanapin natin yung total hourly cost. So to find that cost, the formula would be average number of printers down times cost per downtime hour plus cost per technician hour. So ano ba yung value ng average number of printers down natin? So ang value nun ay yung sinolve natin na pangatlo kanina, which is yung 0.64. Then, ita-times natin siya sa $120, which is yung bagong given value. Then, ipa-plus natin siya sa $25 na galing din dun sa given na value na bago. Then, magka-come up tayo sa total hourly cost na $101.8. Next is, as you can see in this slide, pinapakita naman dito yung solution sa finite population ng Department of Commerce. So, andito na yung mga given variables natin with its value. Andito na rin yung mga average server utilization, average number of customers in the queue, average number of customers in the system, and so on and so forth. Hindi lang siya same sa previous na mga sinolve natin kasi yung mga sagot dun kanina ay naka-round up na. Dito, wala pa kasi halata naman na 5 decimal places yung kinuha niya. So, that's all for the finite population model.
Today, I am Byra Hamina Emlo. In this chapter, we will talk about the some general operating characteristic relationships. In this part, we will talk about some general operating characteristic relationships. When we say some general operating characteristic relationships, it is certain relationships exist among specific operating characteristic for any queuing system in a steady state. A steady state condition exists when a queuing system is in its normal, stabilized operating condition, usually after an initial or transient state that may occur. So what is the difference between steady state and transient state? So pag sinabi nating steady state, it is based on the assumptions that all flow conditions and properties of the system are constant with respect time. While transient state is it can handle conditions that change with time and assess the time-dependent impact on thermal and flow predictions. So the both arrival rate and the service rate should be stable in this state. Moving on to Little's flow equations. A third condition that must always be met is average time in system, average time in queue, and average time receiving service. So what is the importance of this formula? The one benefit of these formulas is that they make it simple to identify the other features once one of these four traits is known. This is also important because depending on the queuing model, one of these parameters may be significantly simpler to figure out than the others. These are applicable to all of the queuing system covered in this chapter except the finite population model. More complex queuing and the use of simulation. Arnold's Mapper Shop, Garcia Golding Recycling, or the Department of Commerce. Those there mentioned are the characteristic of practical waiting line problems that occur in production and operation service system. And it says here that it is true when the situation calls for single or multi-channel waiting lines with Poisson arrivals and exponential or constant service times, an infinite calling population, and FIFO service. A FIFO service is a queue discipline, meaning first in, first out, in which the customers are served in the strict order of arrival. So in order to have a queue discipline, they are using the FIFO service. Moving on to simulation. Using the approach of probability distributions such as arrivals and services, many hours, days, or months of data can be developed by a computer in a few seconds. Ina-allow nito ang controllable factors such as adding another service channel without actually doing so physically. And basically, whenever a standard analytical queuing model provides only a poor approximation of the actual service system, it says it is wise to develop a simulation model instead. Invariations of this specific case are present in an analysis. Service times in an automobile repair shop. One of the examples of this is tend to follow the normal probability distribution instead of the exponential, and a college registration system in which seniors have first choice of courses and hours over all other students is an example of a first come, first serve naman. First serve model with a preemptive priority queue discipline. A physical examination for military recruits is an example of multi-phase system, one that differs from the single-phase models discussed in this chapter. So I will give another example, another real-life example. Let's consider a line of people waiting to buy a ticket of a cinema hall. A new person will join the line from the end, and the person standing at the front will be the first to get the ticket and leave the line. It defines here that the recruit must enter another queue and wait his or her turn. The one who develop the model's cases are the operations researchers. The computations for the resulting mathematical formulations are somewhat more complex than the ones covered in this chapter. And many real-world queuing applications are too complex to be modeled analytically at all. When this happens, quantitative analysis usually turns to computer simulation. Computer simulation is the process of mathematical modeling performed on a computer which is designed to predict the behavior of or the outcome of a real-world or physical system.